Hello students. In this session we will talk about using Z distribution as a sampling distribution. And I'm taking the example of diameter of tennis balls. According to the International Tennis Federation, a manufactured tennis ball should have a diameter between 6.54 to 6.86 centimeters. Now, taking a case of a large factory that is producing tennis balls, let's assume that the manufacturer is claiming that the ball that they are producing in their factory has the mean diameter of 6.7 centimeter with a standard deviation of 0.3 centimeters. Now, taking this example, the very first step is we need to check with the assumption if the manufacturer is claiming that the diameter that they of the balls that they are producing follow normal distribution. Let's suppose that they are giving along with these two values of mean and standard deviation this important assumption as well. Therefore, we can say or restate the behavior of random variable x, which is representing the diameter of tennis balls, follow normal distribution with mean 6.7 centimeters and standard deviation of 0.03 centimeters. So if we would indicate it as variance, we need to just raise it to square. So this is how we do it. Now let's take, these are the cases of picking up a tennis ball at random from the production lot. It does indicate that we are referring random variable x. And let's suppose in part A, we are asked for what if a tennis ball is picked at random from the production lot and it has the diameter below 6.55 centimeters. Similarly, the probability that a randomly selected tennis ball has a diameter exceeding 7.3 and what is the probability that a randomly selected ping pong ball has a diameter between 6.4 and furthermore the diameter unknown diameter of the ping pong balls that are representing the middle 60% of the production lot in terms of the least and the maximum diameter, and this is how we state it as between what two values symmetrically distributed around the mean will 60% of the ping pong of the tennis balls fall. Now let's start with the working. We will be using the same formula to get each value of x transformed to z. So taking the very first part, the given value of x is 6.55. We get the mean value of 6.7 subtracted from this and then divide this by the standard deviation value. And ultimately we will be getting the answer of z value as point minus zero point 0.5. And referring the table for the probability corresponding to minus zero point 0.5, 0 is 0.3085, you can see. So this is our answer. So there is a 30.85% chance of the probability of 0.3085, that is representing the probability that a randomly selected tennis ball will have a diameter less than 6.55 centimeters. Now, dealing with this part, again we will make a substitution of x values as 7.3, take away 6.7 divided by zero point 0.3 would give us 0.6 as the difference, and this is 0.3, and that would give us z value of 2. So probability that the z value is greater than 2. Now you can refer the previous lecture where we have seen that when greater than sign is given along with the z value, the way to answer this is probability of z greater than 2 can be obtained or estimated as 1 minus probability of z less than 2. So referring the table, this is 0.99 something. This is 0.9772 across z value of 2. So 0.9772, it would give us 0.0228 as the answer. So there is a 2.28% chance that a randomly selected tennis ball may have the diameter above 7.3 centimeters. Now, moving to the next part, we will first get it transformed as z1 equals 6.4 minus 6.7 divided by zero point 0.3 gives us minus 1. You can check with the help of a calculator. Similarly, z2, which is the upper bound, will be based upon x value of 7. Take away 6.7 from that, divided by standard deviation of 0.3. Now, 7 minus 6.7 divided by zero point 0.3 would give us 1 as a z value. So we take the upper bound first, then we take the lower bound, and then take the difference of the probability associated with these two values of z. So probability across z equals 1, we can check again from the table. This is 0.8413, and across minus 1, this is 0.1587. So 0.8413 take away 0.1587 would give us 0.6826. So there is a 68.26% chance for a randomly selected tennis ball to have the diameter between 6.4 and 7 in centimeters. This is what it does mean. Now, answering next part, we need to consider drawing of a sketch at the first place, because this time what we are given that this set or this coverage between A and B under this normal curve should be of 60%. and these two borderlines of A and B should be at the same distance, because the word symmetrically distributed around the mean value indicate that these two borderlines should have at the same distance bit, from the center or mean line. So I'm going to draw this curve, and this is the mean line, which is in our case representing 6.7. We don't have any information about this, but what we know that within A and B, this is the symmetric area of 60%. So area covered between zero point 0.6, covered between A and B is zero point 0.6, will indicate that this is 0.3, this is 0.3. This borderline divides the curve into two equal halves. So if this area is 0.3, then this area should be zero point 0.2, and this area should also be 0.2. Now what we do, we try to understand the working, the way we need to work the answer. So previously what we are doing, x was given, we were transforming it to z, and we were locating the z probability across that value of z. Now we will follow the opposite path. Probability of z is given as 0.2 over here. We will get it transformed to z, and then in fact after locating z value corresponding to 0.2 probability from the C table, we'll get it transformed to x using the same formula. So if you go to the table and try to find out the probability of 0.2, over here you can consider, or you have to consider necessarily, that the probabilities are given inside the table, not outside. Student may come up with this error that they take this 0.2 probability what we are given in the question as the z value. So you need not to do this error. Try to find out the probability nearest to 0.2 from the table, and you can take notice of this, that when we go to row of minus zero point 0.8, this is the probability nearer to, in fact nearest to 0.2, which is our target. So 0.2005 is this one. The neighbor values is relatively smaller. 0.1977 is relatively more away from the target value of 0.2 probability as compared to 0.2005. So 0.2005 is much closer. So we need to read out the destination. You can consider this as a street number, and you can consider the column as a house number. So minus zero point 0.8 is the row, and this is 0.80, 0.81, 0.82, 0.83, and 0.84. C. So collecting these two values, the location of this z value or probability of 0.2005 is at minus 0.84. We know that the central value in terms of z is 0 if these two borderlines A and B are at the same distance from the center, and if A has a z value of minus 0.84 and the central value is 0, then this B should have the z value of plus 0.84. So central value is 0 and the two borderlines are at the same distance, means once you determine the lower bound value with the negative sign, the same value the upper bound should have with the positive sign. Now, considering the formula z equals x minus mu divided by sigma for lower bound value of z, which is minus 0.84, the corresponding value of a is an unknown, x is an unknown value, or a is an unknown value of x we are given. This is 6.7, the mean value, divided by standard deviation of 0.30. We first multiply these two together and then we get the negative answer. We then move this minus 6.7 to the left hand side. So this would be the entire working. This would give you the value of A. And the value of A is 6.448. Similarly, the computation of B, which is upper unknown bound for x, can be performed as taking the positive value of z of 0.84. In place of x, we substitute b minus 6.7 divided by 0.3. And again, this 0.84 is to be multiplied with this 0.3. Then we add 6.7 to the answer, and this would give us the b value of 6.952. So this is the use of z distribution with all the possibilities whenever we are picking up only one observation from the population and referring that value as x.